Good afternoon, everyone. I'm Chathuri, a PhD student from Transport Research Center, University of Technology, Sydney. Today, I'll be presenting my PhD work, that is use of rubber intermixed ballast stratum (RIBS) for enhanced longevity of rail infrastructure. I was a practicing engineer in Sri Lanka before I started my PhD, and the valuable experience I obtained, especially working in the Southern Railway project in terms of design and construction, is very helpful and encouraged me to study further in the area of railway geotechnics. With that, let's move to the today's topic. In the world, rail transportation plays significant role in transporting passengers and goods. Because of increasing demand, trains are becoming faster and heavier. Due to the heavy axle loads and the higher frequencies, tracks are degrading faster. That can be due to the ballast degradation, differential settlements, lateral deformations, or mud pumping. It has found that more than 70% of ballast fouling happens due to the ballast breakage. Globally, more than 25 million tons of tires reach end of life every year, but only 2% of them utilized for civil engineering applications. More than 30% remains illegally dumped or stockpiled, causing serious environmental and social hazards. These are some of the examples where tire-derived aggregates, TDAs, are used in civil engineering. They are used in rubberized asphalt concrete or outdoor play areas because they are cost-effective, resistant to crack, and durable. They are also used in embankment fillings and retaining wall back fillings due to the light weight of this material. TDA also used in the alongside of the tracks to attenuate the noise and vibration in near building areas. In my project, what I'm doing is use these rubber granules derived from waste tires and mix with the conventional ballast material and then come up with this new material, rubber intermixed ballast stratum. We simply call it RIBS. So the aim of this study is to promote the concept of using rubber granules derived from waste tires as elastic aggregates blended with the traditional ballast particles for better performance of rail tracks. In this figure, you can see the particle size distribution of the RIBS material, that is according to the Australian nominal 6th graded ballast specification. First of all, we had to select optimum size for the rubber granules. The numbers you see here in this slide are the sieve sizes of gradation curve. If we replace the smaller ballast particles, which are smaller than 9.5 millimeter with rubber granules, it can cause ballast falling. If we replace larger particles that are larger than 26.5 millimeter with rubber granules, it can reduce the stiffness of the ballast matrix. We can't compromise the stiffness of the larger particles because these larger particles share most of the applied loads. Also, we observed that the rubber particles obtained from the normal tire threading process are different in shapes. Larger particles are planar and flaky, but the particles in between 9.5 to 19 millimeter has the angular shape same as the ballast material. Therefore, with these particles, RIBS shows effective particle interlocking capacity, minimal impact on ballast fouling, and the minimal impact on the reducing the stiffness. Also, I compared my experimental results with previous studies. They have used the similar ballast gradation for rubber particles, but we can say that the rubber particles in between 9.5 to 19 millimeter perform better in terms of reducing dilation, reducing breakage, and this particle has the minor effect on reducing the shear strength. These are the laboratory tests I conducted for the RIBS using the large-scale triaxial apparatus. The sample size is 300 millimeter in diameter and 600 millimeter in height. We did the test for static and cyclic loads under confining pressures between 10 to 60 kilopascal. That is generally the track confining pressures. The frequency of cyclic loading is 20 Hertz. That is similar to the train speed of around 140 kilometers per hour. We did the testing for RIBS with different percentages of rubber, 5, 10, and 15%, and then compared with the conventional ballast material. In the table, you can see the basic properties of the sample. The axial load I applied is representing axial load of 25-ton trains. When we modify the material or come up with a new material for the ballast layer, it should perform similar or better compared to the traditional ballast layer. So these are some of the important functions of ballast layer. So the ballast shares substantial loads carried by the tonnage, ensures track stability and drainage, absorbs noise, vibration, and provide adequate electrical resistance. These are some of the results for the static loading test. We observed minor reduction in effective friction angle, but the significant reduction in the dilation angle. Reduction of effective friction angle is less than 6% when we increase the rubber up to 15%, but we observed around 50% of reduction in the dilation angle with the 10% of rubber. In this figure, you can see the stress strain diagrams. Can see that the increase of rubber content reduces the peak deviator stress and shows larger initial compressions before the dilation. The reason is the rubber compresses initially and attains to a densified particle arrangement. So therefore, we can't keep increasing the rubber content in the ribs mixture. So there should be an optimum limit. The first figure here is the definition of the ballast breakage index BBI. That is what we use to quantify the ballast breakage. As in the second figure, you can see that the ballast breakage index is decreasing with the increased rubber, which means rubber reduces the particle breakage happens due to the applied loads. The third figure is another method of quantifying the ballast breakage, that is Marcel's breakage index. We observed more than 70% of reduction in breakage in the larger particles, which are larger than 26.5 millimeter. So we can say that ribs perform better in reducing the ballast breakage. Here you can see the shear stress strain diagrams and the energy absorption during the static loading. Ribs shows reduced peak shear stresses at larger axial strains due to the increased ductility of the mixture. We observed around 1.3 times of increased energy absorption capacity with 10% rubber. Because of the increased energy absorption capacity of the ribs layer, the energy that goes to the below layers will be reduced. That is also another advantage of this material. Then we did the testing for cyclic loads. Here you can see the loading procedure. The first two figures from left to right show the variation of axial strains and the volumetric strains against the number of cycles. And the third figure shows the variation of the rate of permanent axial strain. Here we observed reduced axial strains or the settlements and then reduced volumetric strains or the dilation with the increased rubber. With 5% of rubber, the reduction of settlements is marginal, but when we increase the rubber content up to 10% or 15%, the reduction is significant. Reducing the axial deformation and the dilation means it reduces the track instability, and that is obviously a positive thing. Rubber delayed the specimen's attaining shakedown, but ribs attains a stable axial strain rate at a reduced axial strain. It is obvious that the accumulation of plastic strain at a slower rate is better in practice to reduce track maintenance cycles. In other words, that means the ribs increases the track longevity. In this slide, you can see how rubber affects the resilient modulus, damping ratio, and the energy dissipation capacity. Increase of rubber decreases the resilient modulus, but increase the damping ratio and the energy dissipation capacity. Resilient modulus is an important parameter in track design because it is an indication of elastic response of the granular material under repeated loads. Generally, resilient modulus should be larger than 200 to 250 megapascal for track design. So you can see here, if we increase the rubber content more than 10%, the resilient modulus may not be sufficient. Also, increasing rubber more than 10% does not make considerable effect in increasing the damping ratio and the energy dissipation capacity. Together with these results I discussed so far, and also we analyzed the material for stress dilation behavior and the modulus degradation, and then came up with the optimum rubber content to be utilized in this ribs mixture. That is 10% by total weight. This is about the proposed field testing for ribs with optimum 10% rubber. We are doing this trial track with the collaboration of Sydney Trains at Chullora Technological Precinct, New South Wales. We'll be able to complete the track construction in January next year. From this field trial, we'll be able to study the effect of rubber in reducing the vibration and noise, and also we can identify the practical benefits and the limitations of this ribs material. This is the summary of track design for ribs and the conventional ballasted track. You can see the reduction of risk in ribs tracks compared to the conventional ballasted tracks in terms of stability, deformation, and the ballast breakage. Actually, we don't have to change the track formation to use this ribs material replacing the conventional ballast layer, but there's a possibility of reducing the required layer thickness by using this material. As a conclusion, I can say that the other than the better performance of rail tracks and the increased longevity, which I discussed so far, ribs also provide a solution for non-biodegradable waste material from the tire industry at a lower cost. Ribs also help to preserve the natural landscapes by less quarrying for tracks. So that is pretty much about the experimental outcomes of my project. And I want to acknowledge my supervisors, Professor Buddhima Indaratna, Dr. Yujichi, and Professor Cholachat for the continuous guidance and support. And also I want to thank ICGE Colombo 2020 Organizing Committee for giving me this valuable opportunity. Then I acknowledge our team at Transport Research Center, University of Technology. Also, I want to thank my industry partners, Bristol Corporation, Sydney Trains, Australasian Centre for Rail Innovation, ICRI, and Australian Research Council, ITTC Rail, for the financial and technical support. Thank you so much.